All right, so that brings us to the threshold. And the threshold is going to be the point where we either find out whether or not the action potential is going to happen or not. The threshold typically is about 15 to 20 millivolts higher than the resting membrane potential. And if that number is reached, then we have an action potential, and it is an all or none phenomenon. If we do not reach the threshold, then there is no action potential. Therefore, that turns into just a little graded potential. So propagating an action potential just simply goes like this. As the action potential serves as a signaling device, the sodium influx is causing a local current, and the influx of sodium with that local current is going to go all the way down the entire axolemma. And as it goes along the entire axolemma, it'll cause all of our sodium channels to open or close, which is generating the action potential along the entire cell, not just a piece or part of it. So as far as all action potentials, they're all going to be alike. The intensity, the stimulus is all going to be exactly the same. What we can do, and if we want to find out about a strong signal or a strong stimulus versus a weak stimulus, has to go in terms of frequency. Now, I know we've talked about this in class a couple different times, how frequency changes the stimulus, but a strong stimulus is just going to basically show more action potentials, whereas a weak stimulus shows less action potentials. Let me show you what I mean by that. Here is a chart showing the action potentials. You'll notice that resting membrane potential is at -70, and they reach up to +30. Notice that all the action potentials are exactly the same. There is no variation between 1, 2, 3, 4, or these 8 or 10, however many is in this time frame. What we'll notice is, though, however, here is the intensity of our stimulus. If we do not reach the threshold, there's no observable action potential. If we barely get over the threshold, then that's a weak stimulus. Notice there's only 4 in this time frame. Over here we have a much stronger stimulus. That means we're going to have multiple action potentials within the same time frame maybe that it would have caused for this one over here. Doesn't change what the action potential does, it just changes how fast they're sent. There is something called a refractory period that goes along, and as the refractory period happens, it just basically says another action potential cannot start until this action potential is finished. That's why I mentioned it as an all or none. Notice that they're complete action potentials, and they are an all or none piece that has to happen, and if it doesn't happen, then of course it was a graded potential. So what causes action potentials to be sent better? Well, pretty simple. If we need to have action potentials being sent faster, we need to send it through a better insulated tube. So the conduction velocity is always going to be influenced by the degree of myelination. How much insulation do we have on the outside of there? Another thing that can change conduction velocity is the diameter of the axon. Just think about this. If I wanted to put out a fire, am I going to use a garden hose or a fire hose? The larger the hose, the more water can get through in a short amount of time. Same deal here. The larger the axon diameter, the more information can get through in a shorter amount of time. So those are the two major things to look at when we're talking about conduction velocity, is how big is the fiber and what is the insulation like. Myelin sheaths are always going to insulate. They're going to prevent charges from getting out. However, there's something called saltatory conduction, and saltatory conduction happens because of those myelin gaps. If you remember what the appearance of those myelin sheaths look like, the Schwann cells were little bubbles. That means that there's gaps in the coverages. That gap seems like it might not be a good thing, but it actually is positive, because what it does, it allows for this saltatory conduction to take place. Let me show you the picture. Up top is a bare plasma membrane that doesn't have any axon coverage, so there's no myelination. You can see that the signal is going to die out over the course of time. This is a non-myelinated axon that allows for conduction to take place because of these voltage-gated channels. Notice as the signal dies off, it gets resparked, and then it picks up again, starts to die off. This is a fair way to do it, but it's not going to send it as clearly as if I have myelin sheaths or these Schwann cells down here on the third one, where I have a stimulus. It's going to be carried out for a long distance and travel really fast. Then in the gap, I have saltatory conduction taking place, which sparks it up and allows for that conduction to happen again. Much more effective. So this kind of tells us a little bit about why something like MS is such a damaging disease. What MS does, multiple sclerosis, it actually attacks your myelin sheaths. And if we attack the myelin sheath, then you can kind of picture what's going to happen here. We're going to destroy the insulation. Transmission of signals starts getting crossed. That's what causes the shaking. We're not able to send effective information from the brain to even vital organs, which would cause them to start shutting down. So we can see it becomes very, very much more problematic than any other little disease. All right, classification of fibers. I've already said the diameter, degree of myelination, speed of conduction. So if you want to look through these, there's 3 classes of fibers. There's group A's, group B's, and group C's. They're just in relationship to size. So larger diameters are group A, smaller diameter group C. And if you look at their transmission signals, you can see transmitting at 150 meters per second. If you figure that, my body is about almost 2 meters tall. That means I can send information from my head to my toes and back to my head 75 times in 1 second. Think about that for a second. 75 times in 1 second you can send information back and forth. Remember how specific we said these fibers had to be? They're sending and receiving signals rapid and specific, and that is a proof right there. These smaller fibers are going to be typically autonomic nervous system fibers, and if you consider their location, they're basically right around the trunk, and so they don't need to travel very far. So it doesn't need to be quite as fast. All right, as far as synapses go, we're looking at some communication networks between neurons and another cell. This is basically just like our neuromuscular junction, a synapse or a junction where 2 things meet together. The synapse, we can give a little different examples now because we're not talking about muscles. Instead, we're talking about synapse between other nerve cells. So here we see an axodendritic, an axosomatic, or axoaxonal. What basically we're doing is we're making up medical terms to connect 2 nerves together. An axon to the soma, or the body of the cell, an axon to a dendrite, axon to dendritic, axoaxonal, axon to axon, dendrodendritic, dendrite to dendrites, soma to the dendrite. You get the drift. When we're looking at this in terminology also, you can remember that there is something called presynaptic and postsynaptic. That just simply means before the synapse or after the synapse. But as we've mentioned before, all neurons are going to function as both. That means that they're both going to be presynaptic and postsynaptic. It really just tells us that we can share information. So if you think about it, if I whisper to you in the front row a piece of information like the number is 10, and then you turn around and share it with the person behind you, when I shared that information with you, I was the presynaptic neuron and you were the postsynaptic neuron. But then when you turned around to share it with the next person, you became the presynaptic neuron and they became the postsynaptic. It's like that old game Telephone. You used to whisper something in somebody's ears and see how long it would take to go to the back of the room, and then by the time he gets back there, it's a completely different sentence. Same sort of thing here, except for the transmission of information is going to be perfect. It's specific and it's rapid. So here's some connection points between these cells. The neurotransmitters, we've already discussed neurotransmitters at length, and I'd love for you to read over these neurotransmitters. So I'm going to kind of click through and just make sure we're fully understanding. Neurotransmitters are the language of the nervous system. They come in lots of different ways. There's 50 or more that have been identified. The one that we used mostly was this acetylcholine. We know a lot about it. We know it's at all neuromuscular junctions. That's why we talk about it. There are biogenic amines. There are chemical structures like substance P's or pain signals, and endorphins, which can block pain signals. There's endocannabinoids, and if you have interest in talking about these, endocannabinoids, they sound just like that. Researchers actually found them when they were trying to figure out how THC was affecting the body and what benefits people were having from it. So they found this endocannabinoid system, which actually has the same receptors as THC, and it acts very similar to what THC, which of course you guys know, that's the active and psychotropic ingredient within marijuana. However, the neurotransmitters that we're conducting or that we're reducing or producing in the body are just basically going to help with things like learning and memory, development, appetite control, suppressing nausea. And if you think about the things that marijuana does, kind of the same results, right? Controlling appetite, giving the munchies, suppressing nausea, neural development, making you hungry. The other thing is it kind of works with memory, right? Takes the memories out. The endocannabinoids obviously are going to be there working within the brain without the psychoactive effects, right? So how do you classify them? They can be either excitatory or inhibitory. That just simply means that they cause a depolarization or they cause a hyperpolarization. They get you closer to the threshold or push you farther away from the threshold. The other thing is they can be direct action or they can be indirect. If they're direct, it just simply means the neurotransmitter binds to the ion channel and it opens up. For instance, think about what acetylcholine did. It binds to the channel and caused it to open up. The indirect action was the neurotransmitters that are working with second messengers, and we didn't focus too much time on second messengers, so I'm not going to do the same thing here, right? Into the integration, I want you to kind of skip over this. We're not going to see this on the exam. Discharge zones facilitated. You can read about it, but it's really not impressive for your exam. But the final thing that I want to cover is these circuits, and these are 4 different types of circuits that go in your body: diverging, converging, reverberating, and parallel after discharge. The first is the diverging circuit. You can see there's one input and a whole bunch of outputs. This is showing an example of how one single neuron in the brain can activate hundreds of neurons, even thousands of fibers of muscles throughout the body. This is a diverging circuit. A converging circuit, you can see, is a whole bunch of inputs and only one output. This would be why we can have different stimulus that elicit the same memory. If I smell an apple pie, it reminds me of my grandmother's house. If I see an apple pie, it reminds me of my grandmother's house. She was an old Pennsylvania Dutch woman who loved to bake, and she had beautiful Granny Smith apple trees in her backyard, and she would pluck those things, and she'd make these wonderful apple pies and apple turnovers and apple butter and whatever else you can think of. But that is an example of a converging circuit, how there's many inputs but only one output. There's a whole bunch of stimulus that all ends up at the same memory. The next is reverberating, and reverberating is kind of like an oscillating circuit. It sends a signal down and then it kind of reverts back to one of the other ways. This is kind of our repetitive actions. It's rhythmic activities like walking or breathing, our sleep-wake cycle. This is a pretty typical action. Then our last one is the parallel after discharge. And the parallel after discharge just simply says there's one input and one output, but there's a whole bunch of ways to get there. This is basically how we utilize mental actions like mathematic calculations. If you think about it, if I told you the answer is 10, and I asked you what are 2 numbers that get me to the number 10, you could say 6 and 4, 5 and 5, 8 and 2, 9 and 1. That's a whole bunch of different ways to get there. I gave you one input, the number is 10, and you're giving me one output, the number is 10, but you're having a whole bunch of different ways to get there. These circuits are the way that our body sends information back and forth. So that ends chapter 11. I hope that you have found this useful and this can be used for your exam. If you have any questions, please feel free to email me, again, t.jackson@dtcc.edu.